There is an object in the universe that looks exactly like a black hole, but doesn't break physics. Black holes have terrified physicists for a century, not because of what they do to space and time, because of what they do to the laws of the universe itself. They create a place where physics simply stops working, where equations tear apart, where reality has no answer. It is called a gravastar, and the answer to what it is changes everything we thought we knew about the most extreme objects in the cosmos. The conventional explanation for what happens at the end of a massive star's life is this: gravity wins. A star 10 times the mass of our sun burns for millions of years, fusing hydrogen into heavier elements, and then, in under 1 second, it collapses under its own weight. The core, denser than anything we can create in a laboratory, keeps compressing until matter itself gives way. Space curves past the point of return. A singularity forms, a point of infinite density, no physical dimensions, a place where the known laws of physics break down completely. But there is one thing this explanation cannot account for. Everything that falls into a black hole vanishes, gone, destroyed. But physics says information cannot be destroyed. What if the singularity was never the only option? The alternative begins at the same moment as the black hole scenario. A massive star reaches the end of its life. The core collapses. But this time, something fights back. Atoms and particles are compressed so violently that they stop being matter entirely. They convert into pure energy. A bubble forms. In a fraction of a second, this energy bubble collides with the still collapsing mass above it. The unstoppable force meets the immovable object. Neither wins. The interior of a gravastar is empty. Not mostly empty. Perfectly, completely empty. The most gravitationally extreme object in its region of space, and its inside is nothing. But this nothing is not ordinary nothing. In modern physics, particles are not solid objects. They are waves, vibrations in an invisible cosmic fluid that fills all of space. The apparent emptiness of space is not empty at all. It is an ocean. Your room right now is 99.98% this vacuum fluid, the space between every particle of air, every atom in your cells. What keeps this perfect interior in place is the shell. The shell is made of a form of matter that has no name. It has never been observed. It sits at the absolute outermost boundary of what nature can construct. It is unimaginably thin, so thin that individual atoms appear enormous beside it. Yet stretching it by just 1 meter would require the total energy output of a supernova. The shell of a gravastar is the coldest object in the universe, 1/1000th of a degree above absolute zero. At that temperature, the oldest light in existence appears brighter than the shell itself. The violence of the collapse compressed the cosmic fluid itself to the absolute physical limit. The result is a supercompressed void, the most extreme vacuum energy density in the universe. This supercompressed vacuum pushes outward against the shell with everything it has. The shell pushes back. Neither yields. An eternal standoff between two absolute limits of the universe. A cosmic soap bubble that cannot burst and cannot collapse. But here's what nobody expected. From the outside, a gravastar is almost identical to a black hole. Both are dark. Both are massively dense. Both curve space-time so severely that nothing escapes. The difference is invisible. And then, something changed. In 2017, the Laser Interferometer Gravitational Wave Observatory, LIGO, began detecting gravitational waves, ripples in space-time produced by the most violent collisions in the universe. When two black holes merge, they produce a specific signal, a sharp impact and a rapid decay. Physicists described it as a drumbeat, a heavy, single blow that fades. But a gravastar has a physical shell. When two gravastars collide, that shell reverberates. The gravitational wave signal should carry an echo, a faint ring trailing behind the initial impact, like a gong struck in an empty hall. Black holes strike like a drum. Gravastars ring like a gong, and they leave an echo. Scientists are now searching for that echo in the gravitational wave data collected since 2015. Every merger event is being analyzed. The answer may already be in the data. We may not yet have the instruments to hear it. Gravistars were first proposed in the year 2001. For more than 2 decades, they have remained at the edge of serious physics, theoretically valid, observationally unconfirmed. Right now, somewhere in the universe, 2 massive objects are spiraling toward each other. Their merger will send gravitational waves across billions of light-years of space. Those waves will reach Earth. Instruments will record them. Scientists will search the signal for an echo. This is not just a story about gravistars. It is a story about the distance between what physics permits and what we are capable of seeing. The universe is not obligated to show us what it contains. It only offers clues. Black holes were considered physically absurd for more than 50 years after their first theoretical description. Almost nobody believed they were real. And then, slowly, the evidence accumulated until we photographed one. They may find nothing, or they may find the faint, trailing ring of a gong. If they do, what else have we been misreading as black holes for the past 100 years?